All right, so let's get back to a question that Nathan asked earlier.
Oh, the difference between centripetal and centrifugal?
All right, so what we're dealing with here is centripetal versus the other one. Now, I tend to pronounce it centripetal and centrifugal. I have been in conversations where people do not hear the distinction in the way I say them. So the Sasson will emphasize it more, and I think it's more of a British pronunciation of centripetal and centrifugal, because it's a lot clearer, but I tend not to do that, but I'll flip back and forth. So centripetal or centripetal, centrifugal or centrifugal. Now, let's look at the roots of the words. Center. But then we come into these parts right here. What English word has F-U-G in it that would have the same root, basically the same root?
Fuge? No?
Is that a word?
No, I was thinking about centrifuge.
Fugue. That's not.
I don't think fugue, but it's possible it does come from it.
Music.
We're just making up our words. Something that means away from? Is that what we're
In a
doing?
sense. You escape from prison, what are you called?
A fugitive.
Okay.
Because they're going away. Tempus fugit, anyone familiar with the expression?
Nope.
It means time flies.
What's the expression?
So this is something trying to get away from the center.
Oh. So,
Centrifuge.
you said,
Center fleeing, so
you said tempus fugit.
yes.
Okay, I thought you said tempest, and I was curious. That's Latin, isn't it?
Yes.
Okay.
Occasionally I hear it on TV shows where somebody says it. All right, DET. What word in English do we have today that has that same root and same basic meaning?
Pedal?
What'd you say?
Pedal?
I don't think so.
I don't know.
Petrie.
Yeah, give us
Man,
a
I'd
hint.
be shocked if that is too, but
Give us a hint.
But
two teams come together.
Competition?
Competition.
Oh,
Competition is the same root. This is center seeking. In competition, you have two groups that are seeking each other. Center seeking. This is the huge difference between the two. So if it's pointing towards the center, it's centripetal. If it's pointing away from the center, it's centrifugal. Now, where does centrifugal show up? Some textbooks will just call it sometimes refer to it as a fake force or a false force. If you're in a car and you're going around a curve, it feels like you're being thrown to the outside. You're not actually. But what you are in is a rotating reference frame. You're in a reference frame, the car, which is accelerating. And so if we did the physics based upon your point of view, there would be some force that we would have pointing outwards. But if we did it from the point of view of the ground, there's no force pushing you outwards. There's just a force holding you in.
And you just want to continue on your forward path, but the car pulls away from you.
Absolutely.
Related to that, I remember as a kid playing Roller Coaster Tycoon, and there was something called G-force, which supposedly was related to like the amount to which the person is being thrown to the side of the car in the roller coaster that you built, and the more of that you have, the more they vomited in the park.
Oh.
Side note. However, it seems like that's what this is getting at. Is it all called G-force? Either I'm misremembering it or that's an incorrect term.
G-force generally is a reference to if you're experiencing 2 G's, that means the acceleration on you is twice the acceleration due to gravity.
It's like a measurement more
Yeah.
than a unit.
It's a shorthand, because at a certain number of G's, you black out.
I think it's like 11, isn't it?
It
It depends on the person, but it's definitely above
well,
8 or
that's
9.
come up.
Isn't Roller Coaster Tycoon like a game we did like in middle school? Or is it, like I remember building roller coasters, but I don't know. Okay.
Yeah, did they look like
They-
lemons? Like, did people look like lemons? Because that sounds so familiar. Or am I thinking of
Did
another
they
game?
look like lambs?
No, I played Roller Coaster Tycoon 2 and avoided all of the others because I was dedicated to it, so maybe.
So what you're saying is if you played Roller Coaster Tycoon 1, you are just,
I,
you are dirt?
no, I am not saying that.
Did anyone else hear that? All right,
We should
So-
try and trick her into playing the first one. So.
acceleration of blackout in fighter pilots. The source that I have here says 4 to 6 G sustained for more than a few seconds would cause blackout. Potentially from visual impairment to total blackout. The standard G suits, the one that the fighter pilots use so that they don't do that, looks like they're set for 5.5 Gs. So will offset that much. And it looks like somebody survived 6 Gs, so that is in roller coaster physics. Person will black out if the headward acceleration he or she experiences is 2G.
What?
So,
But they can withstand acceleration on the order of 10 Gs in directions perpendicular to their bodies without permanent adverse effects. That is rather vague what headward means.
I think that means that if you're, like, if you were coming down the bottom of a roller coaster, like from the big drop, and you felt more than 2 Gs there, then you would black out. But if you're turning and you're feeling up to 10 Gs, then you would be fine, I guess.
I think it,
Up to 10.
I
Yeah.
that's quite possible, but headward, I was picturing the way your head is facing
Yeah.
or up.
Yeah, I was thinking like a line up through your body.
from Oxford Languages, it says in the region or direction of the head. So,
That's still vague.
Yeah.
Like, that
Does
doesn't
it,
help.
Are you starting at the center of your body?
You're welcome.
and
It
then
means
going
whatever you
up?
want it to mean.
Or-
I think, what was it? I was thinking about G-force. I don't wanna take up too much time, but isn't it acting on your body to where your blood can't move around enough to circulate, or how does that work? Or is that
That's my understanding of it, that if I go into a dive and then come out of it, I mean, your
Your blood-
internal organs and your blood and
Yeah.
so forth have inertia too, so your blood wants to keep going that way, whereas your body's shooting off this way, so the blood basically leaves your head.
Yeah,
Oh,
okay.
okay, good to know. So people who build roller coasters have a lot more to worry about than just like.
Yeah, unless you're a tycoon too. Then you just have to throw it up in the parking lot. Now, centrifuges, somebody mentioned before, centrifuges as sort of a connection. In my mind, they should really be called centripetes. But I was not asked, so they're called centrifuges.
Well, they, you do usually have the vials like out like that, so you end up with the stuff going like dispersed to down and away from the item.
Yeah, but only because it's traveling in a straight line. The more massive stuff travels,
Yeah.
and there's more inertia, so it's gonna travel farther in a straight line, and the tube just blocks it.
Yeah, so for the argument of it being called a centrifuge, the stuff does move out.
Yeah, I understand I understand what you're saying, and I understand why they came up with the name, but if I could go back and change some of the English language, that would be it,
That would be it.
among many others. Oh, and another place that you can actually use it besides the rotating reference ring. So, overhead view, I have a stopper on a string that I'm spinning around. If I look at the force diagram here, I have this tension acting in towards the middle. And therefore I have a tension acting out on the string. I have a tension acting on this side of the string, and then on my hand, there's a tension flowing out. Typically, we are analyzing that right there. This is the centripetal force. It's towards the center. This, though, officially is actually a force acting away from the center, so that is a centrifugal or centrifugal force. That's a centrifugal force. That's a centripetal. That's a centripetal. potentially, this is the last time we ever talk about this in this course. Rotating reference frame is way beyond the first several years of physics. Maybe senior level physics. And yeah, I mean, so for the most part, we look at the object that is curved, that's turning, and the force. So for the object that's turning, the force is acting on it from usually any other reference frame than itself. The net force is inwards. We're about to erase stuff. Right, so let's take a simple example. I have a table here. There's a hole in the middle of the table, so side view. I have a mass here attached to a string, and at the end of this string, I've got another mass here. I'll call this mass 1 and mass 2. From an overhead point of view, hole in center, I've got a mass here that basically is going to be swinging around in a circle. I'll make mass 1 equal to 5 kilograms and mass 2 equal to 2 kilograms.
Wait, so is mass 1 causing mass 2 to move in this circular motion? Or?
Somehow I get it started. Probably some additional forces. I'm holding on to this while I get the thing spinning. For hopefully there's one set up, so I don't have to thread it. Not that one. Obviously, I have nothing attached to the end here, so let's attach something to the end. All right, so if I just let go of this, this is going to slide like, it slides like that. This is clearly a much higher mass than this is. However, if I get this thing spinning around fast enough, it's not going to fall.
And now it's not.
So similar to what I'm doing that, except I have it on a table just so that I'm not worried about the fact that the stopper as it's spinning around is actually sagging a little bit.
I was so worried about the thing just flinging off and like hitting somebody.
Yeah, that I was trusting.
This is just one of the rubber stoppers.
Oh, okay. Yeah, that was like it.
Yeah, it was a rubber stopper.
Okay, cool. But still. Like that was
She's the ones on there.
So if we do the force diagram here, oh, there's a string right there. Do the force diagram, we have on mass 2, I've got this tension acting this way towards the middle. There's also a weight acting, I guess I'll do from this point of view, this one over here. So I have tension acting to the right, I have weight acting down, I have normal force acting up. Those are the 3 forces that are acting on mass 2. Mass 1, I have tension acting up, and I have weight, that should be weight 1. No, sorry, 2. And I have weight 1 acting down. Obviously, it's not the full force diagram. All I care about are just these 2 masses.
Are we not including friction?
We are not.
Let me make sure I've got this right. Mass 2 is the one up top?
Yep.
Okay.
We are still going through the exact same process as we've done so many other times. We're going through the facades process. Force is done. What is the direction of acceleration? So think about that situation right there. I wanted mass 1 just to be hanging there. What is its acceleration or direction of acceleration of this one right here?
It's outward. Outward from the string.
It would be
So I got outward and a down.
You said the direction of the acceleration?
Yeah,
For mass 1, right?
for mass 1.
There shouldn't
Equal to 0.
Yeah, it should be equal to 0.
Yes. If I had done it right, that the kilogram or half kilogram shouldn't have been moving up or down. It should have just been static equilibrium.
Okay.
Now, in reality, there'll be probably some swaying, but we're gonna ignore that.
So I have a question.
Yes.
So if the magnitude of acceleration is equal to 0, is it fair for us to say that the acceleration has no direction? Because we cannot say it has no acceleration,
Right,
but does the acceleration that is equal to 0 have no direction?
but it has to have a direction because it's a vector. The more apt would be that it's whatever direction you want it to be. That's why the math people came up with the 0 vector. The magnitude is 0 and the direction is something.
Something.
Don't know what it is, but it's something.
Okay.
All right, so this one right here, what is the direction of acceleration?
In towards the hole.
Yes.
To
And
the-
that is the big thing here, is that the acceleration in this case is in the direction of the tension. So in this snapshot in time, it is going to the left. Typically, on a test, what I do is I ask for, do the force diagram and then I give you a moment in time, like when it's on the farthest on the right or furthest on the left, just so that, there's a consistent answer. My equations of motion, I have 3 of them. For down here, it doesn't matter which one's positive. I'll make it positive, why not? I have tension minus weight 1 is equal to 0. Because it's in equilibrium.
You said there's 3. Oh, I guess, yeah, there is 3. Okay.
That has 2 of them. Then I have y2, let's establish those as my positive directions. y2 minus w2 equals 0 because it's not accelerating up or down off the table.
And then ft.
Is equal to mass times the centripetal acceleration. Now when we do substitution, we have a formula for weight. So I can do substitution here. And we have a formula for centripetal acceleration. So we end up with Ft equals m1g, y2 equals m2g. We're not going to use that equation. And then tension is equal to, from the last one, mv squared over r. m2 v squared over r. I'd have to give you the radius, which I did not do. Let's make that a half meter. In this particular case, I have tension equal to the weight of mass 1 and equal to, it is the centripetal force. Notice that when we're doing the force diagram, we are not creating a new force, it's still F-tom. Centripetal force is going to be one or some combination of the others. So solving it, m1g is equal to m2 v squared over r. If I'm trying to figure out the speed in order for it to make this work, solve for v. That's r m1g divided by m2 square root. And now it's a plug and chug exercise. I am going to leave you with one last thought, or one last question. If I have a circular track, so I have an object that's traveling around in a circle. If the track is bent, so if I did a side view, if I looked at this from the rear view, I have the car on the track like this, at some angle. What is the direction of the acceleration of the vehicle?
Is this our cliffhanger, or can we answer now?
Answer it now if you wish.
Would it be similar to what Ian said for the table? It's like going forward, but also inward?
So you're saying that way?
Like this, like in the headward,
Oh,
I guess?
that way?
That way and then in, yeah.
Not in that direction.
Wouldn't it just be static?
You mean equilibrium?
Yeah.
The
Well,
thing is traveling in a circle here, it can't be an equilibrium.
what I mean was, so it's going up on a ramp in a circle.
Traveling, basically traveling,
Oh, it's like a curved
yeah,
Yeah,
ramp,
so.
okay.
We're looking at the back of it, right?
yep, it's the rear view.
Oh,
You're looking from,
oh, like a racetrack,
Yeah.
like a NASCAR.
Yeah, so
Yes.
it should be, I thought the acceleration would be in the direction that it's traveling, but also down towards the middle of the track.
no, and no.
Would it be the center
Those are the
of,
two most common mistakes,
I mean, assuming that the car is not moving down or up the ramp at all, right?
right?
So the direction of acceleration would be at whatever plane the car is on now, as it's moving around, it would be the center of that circle, right?
That's the direction of acceleration. This is not box on ramp problem. Box on ramp, you can put a box there, it's gonna slide down. If the acceleration were that way, then the car would have to be traveling in a circle like that.
Oh.
Cars
yeah.
usually don't do that, cars travel in a circle like this.
Okay, since it's staying in the same place on the track the entire time.
Yeah,
Okay, that makes sense.
so anyway, that's something that we'll hit on potentially Friday. Sorry for those of you who wanted that to be a cliffhanger, you're just gonna have to let the cliffhanger be, you're truly understanding what we're saying.
Anna ruined our cliffhanger for us, but it's okay.
You know, one thing's for
Yeah, you
sure,
should've, I'm glad you